Hi, welcome to mini lesson 11. In this one, we're going to work on doing for a level occupied by bosons the same thing that we did for a level occupied by fermions in the last lesson. So this will be Bose-Einstein statistics and distribution functions. And what we'll see is that this will reduce to Maxwell-Boltzmann distribution in a certain limit. So we're still in section 7.2 of Schroeder. And let's look again at our table from a few lessons ago where we list the possible values of n sub s and e sub s, this time associated to a level that will be occupied by bosons. And so the challenge here is that we have a lot of n sub s values from 0 up to n, and each one has an associated energy value where the energies are just additive. So if you have two particles in the level, it's 2 epsilon. If you have n, it's n epsilon. And so here n can be quite a large number, and so often we let it approach infinity. So because there's so many values in this table, the calculation for the bosonic Grand Partition function will be a little bit harder than it was for fermions. But we can do it. So here we go. This is the definition of the Grand Partition function. And so letting the number of particles potentially approach infinity, the sum extends from little n equals 0 up to infinity. E to the minus beta n e is the energy associated to the integer occupation n. And then we get an n mu as well, because little n is the particle number in this case. And so this sum, we can factor the n out, and that then reduces also to beautiful z is equal to the sum from n equals 0 to infinity of this exponential e to the minus beta epsilon minus mu, all raised to the nth power, right? So just that n in an exponential just pulls out like that. So you might recognize that this is another example of the infinite geometric series that we used when we were talking about the internal partition function for vibrations last week. Again, so this is just a mathematical fact. There's no physics in here, but sum from n equals 0 to infinity of any number r to the n is 1 over 1 minus r on the condition that r is less than 1. And so e to the minus mu is less than 1 if mu is positive. We'll see that it is positive in a few slides. And so we can just evaluate the partition function in that sum directly. So this exponential expression is our r value, and so we just get 1 over 1 minus the r value for z. So it's not super hard, but it does require you to sort of be comfortable with using that geometric infinite series rule. Let's do the same thing for bosons that we did for fermions, namely let's calculate the average occupancy of the level. So this is just what it means to calculate the average. You take n sub s and multiply it by the probability of e sub s, n sub s. And so that's just this expression, which is the Gibbs factor divided by beautiful z. And so we're still going to do that thing where we insert the possible values from the table. So now we're going to sum from n equals 0 to infinity, where n is now representing the number of particles in the system. We have this expression as well. And so if we look at this expression, this is one of the mathematical slash theoretical tools that you're really supposed to learn from taking a thermal physics course. When you see, this is my assertion, after you've had this course, when you see an expression like n e to the minus nx in such a sum, you should really be thinking about connecting that to a first derivative as a possible tool for manipulating the sum to your advantage, right? And so there's no general rule. There's no thing that says you always must do this and there's some sequence of steps you always have to do. But the basic idea is you should be looking for this. You should be aware that this kind of expression can be dealt with in a certain way and that sometimes it helps you. And that's just one of the tools in your toolbox going forward that you'll be able to apply, even if it's not thermal physics, right? So what we can do is set x equal to beta epsilon minus mu. And so in that notation, we'll recall that beautiful z is the sum of n equals 0 to infinity of e to the minus nx. And so you'll just note that the first derivative of z with respect to x is equal to minus the sum n e to the minus nx, right? And so what that allows you to do is to write n bar as 1 over z times the negative of that expression. And that means that n bar is negative 1 over z dz dx, right? So again, what we've done here is to recognize that by connecting this funny expression in the sum to the first derivative of an exponential, we generate a new formula for n bar that turns out to be easy to evaluate, right? So if we just evaluate this first derivative, where I'm just rewriting the last line on the top line here. So now we have an expression for beautiful z from a few slides ago. We can just take the derivative exactly and get this result. So that's just a tool, right? I mean, there's not like there's a physics rule that we use. It's kind of, it's a trick. And it's a trick that you should keep in your toolbox. So let's substitute back in x so that we're back in physical symbols. And as before, we're going to give this average occupancy a special name, little n bar sub BE for Bose-Einstein. So n bar BE is e to the positive beta epsilon minus mu minus 1 is the Bose-Einstein distribution. So this looks just like the Fermi-Dirac distribution, except there's a minus instead of a plus. It makes it easy to remember, but it also makes it easy to mix them up. So don't mix them up. That's a horrible affront to the gods of thermal physics. Let's talk about the properties of the Bose-Einstein distribution. Number one, it's still the average occupancy of the level, but in this case it can be greater than 1, right? Because the occupancy of the level can be anything from 0 up to infinity, this number can be whatever. It can't be negative. That doesn't make any sense. So because it can be greater than 1, it is not in general equal to the probability of the particle occupying a level, right? Because the probability can never be bigger than 1. Now that's an important distinction. So if you remember in the mini lesson about Fermi-Dirac statistics, I made the point that the fact that n bar Fermi-Dirac was also the probability of occupancy was only applicable to fermions. And this is a case where you can see that it's clearly not a general fact. All right. It also includes the reservoir properties of temperature and chemical potential. The most important property of the Bose-Einstein distribution is that it can clearly have a divergence. If e to the beta epsilon minus mu equals 1, n bar BE diverges. That's really significant. It means basically it means there has to be a phase transition. So we'll be talking about that later in the context of the Bose-Einstein condensation. But it also shows you why we're able to accurately get away with using the geometric sum, because this e to the minus beta epsilon minus mu was our ratio in the geometric sum. And the case where epsilon is less than or equal to mu means you've sort of crossed over a divergence, and that's completely non-physical. So we can sort of a priori understand why we were, sorry, a posteriori understand why we were able to use the geometric series without getting into trouble that the ratio might be bigger than 1. So for practice using the Fermi-Dirac and the Bose-Einstein distribution, I think you should look at problems 711 and 712 in the textbooks. They're really plug-and-chug examples. There's nothing particularly tricky about them, but it is useful to go through them so that you're just comfortable using and thinking about occupancies versus probabilities, et cetera, et cetera. And I will have solutions to those posted, even though they're not technically assigned for the week as homework. All right. So let's keep going with graphical discussion. So again, when epsilon equals mu, the Bose-Einstein distribution has a divergence, right? And it actually decays pretty rapidly away from there. As you can see, the occupation can be way, way bigger than 1. You know, as you approach mu, it approaches infinity. As you go to higher temperatures, you have higher occupancy at energies above the chemical potential mu, right? So it gets so at low temperature in the blue curve, there's almost no occupancy at AdV, and then as you increase temperature, the occupancy at that high energy goes up and up and up and up. All right. And so one thing that we know is that the chemical potential is a lower bound on the energy. So energy is always greater than that. Energy below the chemical potential, that should be a mu, not an m, is not physical because it would lead to a negative occupancy. And a negative average occupancy makes no physical sense. You can't have a negative number of particles in a level. All right. So let's just make one more point. We're zooming in really, really close to the divergence for these same temperatures. So look, the y-axis scale has gotten huge. The thing I want to say here, just by looking at this, is what fraction of particles are in the lowest energy state right up on the chemical potential is a really important question. And so the basic idea is, look at the blue curve. In the blue curve, there's almost no occupancy, even kind of close to the divergence over here. You just see a slight upturn, right? And what that's telling you is really all of the particles at low temperature are just falling into this lowest energy level, right? And this is a characteristic of this phase transition, but basically, as you lower and lower the temperature, a larger and larger fraction of all the possible particles are in this one energy level and basically behave as one quantum wave function, possibly containing, 10 to the 23rd particles. Jeez. Sorry. All right. So we're going to do Bose-Einstein condensation in some detail after test 2. But hopefully this idea that all the particles are occupying this lowest energy level is already apparent graphically. So once again, I almost always give graphical questions about this quantum statistical distribution functions, because I think that's where a lot of your physics intuition comes from. And so here's an example of that. I'm going to plot Fermi-Dirac and Bose-Einstein. Fermi-Dirac is in blue. That's the little step function. I plot it for a pretty high temperature, so kBt is 0.8 eV, which is super hot if you calculate the temperature in comparison with room temperature, right? For Bose-Einstein, I use the same chemical potential of 7. And the thing I want to note is that the blue curve and the green curve really agree at energies high enough above the chemical potential, right? They're really overlapping in this region. And so it's interesting to think about, is that what we expect? And it's a little bit misleading to think about it in terms of energy, right? It's not necessarily energy that's the key here, but it's rather the y-axis that's the key, is that as the occupation goes substantially less than 1, these curves are overlapping, right? The question of what energy matters sort of depends a lot on chemical potential, and really the controlling factor is the occupancy. So if we consider the idea that Fermi-Dirac and Bose-Einstein distributions agree with one another, they're the same function for occupations much less than 1, you see what happens. To get an n bar much, much less than 1, you need the exponential in the denominator to sort of be the dominant term. So in other words, this exponential needs to be much, much greater than 1 so that the denominator is huge, and therefore n bar is small. And so that means that whether you have a +1 or a -1 in the denominator is totally irrelevant, And the occupation function is just determined by e to the minus beta epsilon minus mu. Sorry, I'm talking too much. All right, so this is the Maxwell-Boltzmann distribution, or occupation function if you want. And so for very small occupations, you'll always have a Maxwell-Boltzmann distribution regardless of whether you are fermions or bosons. So, and one of the points, if you think back to chapter 6, when we were talking about indistinguishable particles, we made the point that our analysis was really relying on the fact that there were many more levels than there were particles to put inside the levels, right? And that's basically what we're talking about here, that when the occupancy is very small, you have a huge number of energy levels accessible, but very few particles to fill them up. And so you're basically doing classical, almost canonical ensemble statistics out in this occupation range, out in the tail of the distribution, shall we call it. All right, so that's all for today. And in the final mini lessons for before test 2, we're going to talk about a specific application of quantum statistics to the degenerate Fermi gas. So we'll see you next time.